right. Okay. So, last lecture we looked at some basics of thermodynamics, so just sort of some of the governing equations. We're going to add some to that, but it'll be after we get through some statistical mechanics. But for right now, we need to be familiar with one more thing, and that is when we looked yesterday, we looked at two different types of second derivatives. All right, so if I have like a function z is a function of x and y, then the partial with respect to x of the partial of z with respect to y is equal to the partial with respect to y times the, or of the partial of z with respect to x, right? So this is just a property of what are called exact differentials. So this is only true for exact differentials. Okay. So for, of course, for inexact differentials, it is not true. Okay, and we'll take a look at an example of that in just a minute. Before we do that, I want to show you what a full differential equation looks like. Okay, so let's say, for example, we're talking about an ideal gas. Okay, you know, P equals RT over V bar, right? So we can write out the full differential for dP. Okay, so in other words, if I have an infinitesimally small change in pressure, well, that resulted from an infinitesimally small change in temperature and or molar volume. Okay? So an exact differential essentially kind of maps that out for us. We have two terms that show up in this. There is the partial of P with respect to T at constant molar volume dt plus the partial of P with respect to molar volume at constant T dV. Okay, so there are two terms here. All right, this one tells me, so remember, this is just a slope. Right? That's what a derivative is. It's a slope. It tells me how pressure changes with temperature. Right? So if I change temperature, how does pressure change? This dt tells me my step. Right? So if I'm taking and of course dt is technically a small step, right? It's the smallest step as your step size approaches 0, you know. But that's what this is. It's just your step size. So your step size and your multiplied by your slope tells you how much you went up or down. Okay. So this part right here is just, you know, it's just kind of normal stuff, right? How did my pressure change? Well, it changed based on my change in temperature times how pressure depends on temperature. But with a multivariable calculus, you have other terms that show up. So here we've got, how does pressure change with volume? Well, times its volume step. So this dP, you can think about this as like, you know, if you had if you're on a mountain, right? And you guys ever see contour plots? Contour plots? No? No contour plots? Okay, so contour plots where you've got something that's like this. Right, and then at the top we've got something like that. So this is, each one of these lines represents an elevation.
Oh, yeah, yes.
Okay. That's called a contour plot, right? So, okay, so you can think about this as like, you're in this two-dimensional space, right, on the ground, but you also have elevation. So we can think about this as like, okay, I'm going to step, this way, and that's my temperature dimension, and I'm going to step this way, and that's my volume dimension, right? Except we're going to take really tiny steps, okay? So if you take really tiny steps, every surface is just a flat plane with small enough steps. Kind of like every curve is a straight line with small enough steps. All of these are just flat planes at different slopes. So this just tells me that, I'm essentially going to step right, and then I'm going to step up. Or I'm going to step east, and I'm going to step west. Or no, sorry, not east and west. I'm going to step east, and I'm going to step north. So east, north. What was my overall change? So that's how you can think about these differential equations. Okay, this is called a full differential. Full because it's all of the independent variables are in here, right? I've got my dependent variable, pressure, and then I have my independent variables, temperature and molar volume. Okay. All right. So we can actually write out what this full differential is because we know what these are. Remember, we did this one. The derivative of P with respect to T is just R over V bar. We did this last time. And the derivative of P with respect to V bar is negative RT over V bar squared. So if I put all that stuff in, I can get the full differential dP equals, and then we're going to have our T term, which is R over V bar dt, and then our V term, which is minus RT over V bar squared dV bar. So this would be the full differential for pressure in terms of temperature and molar volume for an ideal gas. All right. This right here is general. We haven't specified anything yet until we throw in these derivatives. Because once we throw in this derivative, now we have specified that it's an ideal gas. Okay? But for any material, right? Let's just take liquid water. Well, I change the temperature at a certain molar volume. What happens to the pressure? Okay? And then I'm going to change the molar volume at the same temperature. What happens to the pressure? Right? So we can kind of look through all that stuff. Okay, so that's just kind of a introduction to full differentials, because we're going to make use of these when we look at the state functions for thermodynamics. Okay. All right. So from Calculus 3, we need 3 rules. Rule number 1. This is actually from Calc 1, but we're just going to use it. This is called the inverse rule. Just means that if I flip it, it's equal to that to the minus 1. Notice that the thing that's held constant is the same for both of these. That's important. All right? So we can't have a different thing held constant over here. Okay, number 2. So that one's just from Calc 1. Number 2 is the cyclic rule, and it says oops, I messed up. That's a P, and that's a T. Okay, so this is the partial of V bar with respect to P for pressure, holding temperature constant. So if you look at this, you'll notice that I've got, if I kind of look at these 3 variables in like a counterclockwise fashion, I go P to T to V bar, P to T to V bar, P to T to V bar. Okay, so we're just rotating these 3 variables around. That's why it's called the cyclic rule. I'm taking those 3 variables through this cycle. And that equals -1. And then the third rule is the mixed second derivatives. That is that it doesn't matter the order in which you take the second derivatives. So those are the 3 rules that we're going to use. And the only one that's like probably really brand new is this one right here, right? The cyclic rule, which I have simply stated without proof. So let's prove it. We're going to prove it explicitly for an ideal gas. Okay? So for an ideal gas, we already know this. P with respect to T, dP dt, holding volume constant, is R over V bar, right? Okay, for the next 2, we've got V bar with respect to P at constant temperature, right? We did the inverse of that. So the inverse of that, which was P with respect to V bar. So I can just invert this thing. And then the last one, I need to actually solve this for V, or solve it for T, and then take the derivative with respect to that. So let's solve the ideal gas equation for temperature. So then we can solve this last one. Oops. The derivative of P with respect to V bar is just P over R. Now I want to take all three of those things and multiply them together. So we're going to do R over V bar negative V bar squared over RT. And here, I need to actually make one substitution in order to see how this works. I'm going to substitute in for pressure. I'm going to substitute in what that is, which is RT over V bar. So P over R is equal to T over V bar. And we get that from the ideal gas equation. P over R has to equal T over V bar, because P equals RT over V bar. Okay, so now we got this. Let's start canceling stuff. Let's see what we got. My R's cancel. My T's cancel. My V bar squared cancels with those two, and I'm left with a negative sign, so this equals -1. That makes sense? So that's not a general proof for this rule, but it shows you that it works for an example. This is not a Calc 3 class, so I'm not gonna prove it to you. All right, let's look at one more example. Okay, so is dx equals CV bar of t dt plus RT over V bar dV exact? Is this an exact differential? All right, so how do we solve this kind of problem? Well, we go back to this. This is only true for exact differentials. The mixed second derivatives are equal for exact differentials. So if we look at this, we can write out a full differential for dx in terms of temperature and volume. We can just say, okay, well, this is just the partial of x with respect to temperature at constant volume dt plus partial with respect to molar volume at constant T dV bar. So you can do this for anything, right? I've got dz equals dz dx constant y dx plus dz dy constant, So we can we can write out this full differential. What's important to see is the pattern that emerges. These are equal. So this is the first derivative of x with respect to t. Right? Those are the same thing. Do you see that? This is the first derivative of x with respect to v bar. So I already have the first derivatives. What I need to do is get the second derivatives. So for this one right here, I can ask the question, I want to take the derivative with respect to v bar of the derivative of x with respect to t does this equal the opposite thing, the partial with respect to t, partial x with respect to v bar, like that. Are those equal? If they are, then this is an exact differential. If they're not equal, then it's not. That test make sense? Based on the rules that I've given you? So what we need to do is plug in what this stuff is, right? So I'm just going to plug this in here. Oops, that's a V. All right. So, what is the derivative of CV of T? So this is only a function of temperature. That's what that means, CV of T. If I hold temperature constant, what's the derivative? It's a constant, so 0. All right, now on the right side of the equation, let's see, I'm taking the derivative of this with respect to temperature, holding molar volume constant, so what is that? R over V bar. Right, the derivative with respect to T, that goes to 1, and then I'm holding volume constant, so that's just a constant. Are these equal? No. So, is this an exact differential? No, it is not. Okay, that's enough Calc 3 nonsense. Shall we move back into chemistry? Let's do it. All right, we'll make use of these rules as we work through some of this content. Okay, so this comes from chapter 17. I would really encourage you to take a look at the book on this stuff. It'll be very helpful. And chapter 17, so we're going to talk about statistical mechanics, and in particular, we're going to talk right now about the partition function. So the partition function is typically given the capital letter Q or the lowercase letter q. I know we already used Q for heat. But we also use it for a partition function. Okay? So Q or lowercase q. Capital Q is for the so-called system partition function, and lowercase q is for the molecular partition function. And the first thing that I'd like to do is just kind of highlight what this thing is. Okay? And conceptually, it's very simple. Okay? So, if you have like, I don't know, you probably have a dresser drawer or something, or a dresser. You got a dresser to put your clothes in, maybe a closet. So do you like put your socks in one drawer with your underwear, and then like your t-shirts in a drawer, or does it just go in however? Pants, sweatshirts, jackets. Yeah, I've got like my undergarments drawer, my t-shirt drawer, and then I have like, got some running clothes in a drawer, So we can think about that as like, I have taken my clothes and partitioned them into these different compartments. That's what the partition function tells us. We have, and this is done in an energetic landscape, right? So we have a whole bunch of either systems or molecules or something like that, and we're asking the question, what energies do we put all these things in? Okay, so the partition function tells you about how a system or a collection of systems is partitioned. Okay. All right, and so let's just take a look at this. We're gonna give them all energies of E subscript J. Okay, so J refers to some energy state or level or something like that. Okay. Well, we're specifically going to be looking at energy states. So the jth state has energy E. Okay. Now let's just say that we have. Let's consider states 1 and 2. Okay. So the relative number of systems in energy state 1 and energy state 2 must depend on the energies. That's what this means. So A1 divided by A2. A is the sort of fractional number of systems that are in state 2. A1, the number that are in state 1, has to be some function of those energies. Okay? Okay, furthermore, the ratio of these systems not only has to be some arbitrary function of the energies, it has to be a function of the difference between those energies. So it only depends on the difference between the energies. And the reason for this is because the relative number is independent of where we call zero energy. Right? So for example, if you're looking at partitioning some balls on an elevation, right? You pile them up, right? It doesn't matter if you call ground zero elevation or you call sea level zero elevation. The relative, sort of pile, how many are on the bottom and so on, just matters on their relative elevations, like how many are stacked on top of each other, right? So that's kind of what this means. It doesn't matter where we put zero. This is also true for two other states. Now, the relative numbers of A3 to A1 has to equal A3 to A2 times A2 to A1. Right? This is just math. Cancel out the A2s, and that's what it gives me. So what this means is that the function of E1 minus E3 has to equal the function of E2 minus E3 times the function of E1 minus E2. Right? Because these are just dependent on these functions. We don't know what they are yet. Yeah.
So with A2 over A1, the function was E1 minus E2.
Uh-huh. Oh,
So
this should be E2 minus E3, sorry.
Okay, so the one on the bottom is what is...
Yeah. And that's technically arbitrary. We could have done it the other way, but thank you. Yeah, I need to be consistent here. Yeah, that was just, I mislabeled that. All right, what function satisfies this? That if you multiply these two things together, you add their arguments. You see that? You're taking this, multiplying it by this, and you're adding the arguments together, because if I add E1 minus E2 plus E2 minus E3, I get E1 minus E3. So what kind of function does that? Where if I multiply the function, I add the arguments. The product rule? No, we're looking for a function, not a calculus rule. You don't know? You know this. As soon as I write it, you'll be like, oh yeah. A linear function? No, not a linear function. It's an exponential function. An exponential function satisfies this, right? So if I multiply these two things, what do? I add the exponents. Right? And so then I get that. You knew that, right? Okay, what we're doing is we're getting to the point where we're going to derive the partition function. We're almost there. But now we have a subscript j is equal to c e to the minus beta EJ. So we were looking at relative energies like A2 to A1 or A3 to A1. We can generalize this to A subscript J is equal to some constant. We'll figure out what that is in a minute. E to the minus beta. Beta is another constant, right? EJ. So we throw in these constants. We'll figure out what C is here imminently. And we can figure out what this C constant is by adding up all of the AJs. If I add up all the AJs, then I get C e to the minus beta EJ. I'm just going to add them all up, but I'm going to factor C out of all the terms. So I can just factor C out of this summation. And if we call the total, this total over here, just capital A, just call that capital A, then C equals A over the summation of e to the minus beta EJ. All right. Now the probability that a system will be in the jth state, P subscript J, is equal to the part over the whole. Right? How many are in state J over the total number, right? So this equals e to the minus beta EJ over the summation of all j e to the minus beta EJ, where all the C's kind of get canceled out. We can define Q to be the denominator. This is the partition function. Q is a function of N, V, and beta, where N is the number of systems, V is the volume, and beta is this beta term. Okay, let's just summarize real quick. The partition function tells us what? It tells us how the systems are partitioned, split up, distributed amongst all of the energy states. That's all it tells us. So it is a summation, right? Because what am I adding up here? I'm essentially adding up, this is probability over here. And I'm saying that the probabilities all have to add up to 1, because if I add all these terms up, if I add all of those terms up, I get capital Q over capital Q, which is 1. All right. Now, I think the strange thing is, typically when you think about like a partition function, you might think about, okay, I'm going to put, 10% here, 5% there, That's kind of how you think about a partition function. But this is not that. The partition function is just a number. And it's kind of strange. But hidden under the hood, inside this partition function, is all this stuff. Okay, so let's look at one quick example of something we can do with the partition function. We can calculate the average energy from Q. Okay, the average energy from Q. Okay, so if I want to just calculate the average energy, or the average of anything, really, the way that we do that is we add up all of the probabilities and their outcomes. This is a weighted average. This is how I calculate your grade. For all my classes are weighted averages. It's like exams are worth 60% and homework is worth 10. I would have the probabilities. Those are the weights in that case, 60%, whatever. And then E's are the values, that exam average or whatever. So this is just a weighted average, right? It's how you calculate average molar mass of elements. Okay. So does that equation make sense then? Okay. So we're going to plug in what the probability is. Okay. So we're plugging in the probability. The probability is e to the minus beta ej over q, right? That is the probability. Okay, now what we're going to do is something that's a little bit strange. We're going to take the partial derivative of the natural log of Q with respect to beta. Okay, first, what's the derivative of the natural log of something? It is not e. So if I have like d ln of x, let's see, ln of y. I'll do ln of y dx or something like that. The negative log of y? Well, here, let's just do this. Let's let y equal ln of x. Okay, let's try this. Y equals ln of x. What's dy dx? You remember? It is 1 over x. Yep. Now, what if I had y equals ln of u, where u is a function of x? Then what is dy dx? Have to use the product rule. I mean, not the product rule, the chain rule, where it's 1 over u times the derivative of what's inside. So that's what we're doing up here. I've got the natural log of q. So this is equal to 1 over q times the derivative of q, which is just right? I'm going to take the derivative of q. Let's work with that real quick. Let's just, this is a summation, right? How many terms do I have in this summation? A whole bunch. Let's just take one of them out. And let's just say let's take the first one out. Let's see what this is. What is that? Yeah, it's negative E1 e to the minus beta E1. Is that what you said? Something close to that? Ish? Yeah, ish. Okay. Right, because we're taking it with respect to beta. So beta is the argument of the derivative, so it stays up there. But we have to take the derivative of that, which is negative E1. So in general then, this is just equal to 1 over q, the summation of negative ej e to the minus beta ej. Now, what do you notice about this and that? They're almost the same. What's the difference? The negative sign. So I can put all that together and say that the average energy is equal to the negative of natural log of ln of q with respect to beta, holding n and v constant. Interesting. Okay, so we're out of time. I'll apply this to a monatomic ideal gas and show you I don't know if you remember, but for a monatomic ideal gas, it's 3/2 NKT. I don't know if you remember that at all. You might have seen 5/2, or you might have seen 3/2 nRT as the average energy. Anyway, we'll show you that. In the next lecture. Okay. So